Hi guys, how many are present? 7 viewers already. Like the video, guys. You know it's gonna be good, right? So like the video already. Just 3 viewers now. I'll start in some time. Okay. I need at least 10 viewers. I know we are not getting 10. I am low on sleep. Hi. I'll start in some time. Okay. We need viewers. I'm not sure if he'll join or not. Couldn't solve any. Why Shibe? Why? Hi Ari. Where have you been? I don't think it's 4 viewers, right? It's not showing properly. I think it's more than four. 1049 due to. Well, let's see. You hate, right? Xeoper. You hate, right? See, wrong answer on test 2 happens. Nice, bro, Ari. Wrong answer on test 2 happens mostly when you don't prove. Okay, we have more than 10 viewers. I think I can start now. So I'll start by sharing my screen, okay? So, guys, like the video. This is fake Umnik. He always comes here. Guys, div twos are important, okay? B is in high demand. So I'll first solve B, okay? Somehow B is in high demand, okay? Is the clarity good? So now let me open the folder, streams, this one. So let me try B, okay? I'll try B. This one's- So guys, see, I say always this is purple. I'm just trying to prove to you people that I'm not solving them and then acting like I'm solving new. Okay, see this is purple. Okay, so you'll see the problems. Hi Sachin Gond, how I talk to you. So let's go for B. Another divisibility problem. Name doesn't seem that bad. Okay, Alice and Bob are playing a game. See, you guys say how to prove. In games, you always prove by okay, someone will have a lot of control, like it goes outside you bring it back, it goes outside you bring it back. So you prove such a thing in games, okay? In games you prove such a things, okay? Someone told me this is very difficult to prove or it's intuitive, how do we prove this, right? But maybe it can be proved. I mean, I don't think games will have, if you can solve it, games can be proved probably, right? uh, Alice and Bob are playing a game in which Alice has given Bob a positive integer x less than or equals to 8, okay? Alice has given Bob a number x. To win the game, Bob has to find another positive integer y such that x concatenation y is divisible by x plus 5. Damn, sounds weird. Here xy is the integer formed by concatenating x comma y in integers x equals to y. Okay. So it's nothing but x into the 10 power number of digits in y plus y, right? Okay, this is not games. Sorry, this is not like a taking turns kind of game. uh, I'm taking that back. This is just find such an integer, and given that it always exists, it can be shown that it always exists. So whatever the y is, so whatever the x is, There is some integer y that satisfies this thing, it seems. So first let's try to write it for what it is, okay? Don't spoil the problem for me, okay? A bit. Ask if you have a genuine doubt. If you have solved the problem, don't tell those things. If you haven't solved, if you're trying along with me, that's fine. Because two people trying and getting something is good. Uh, Two people trying and getting something. What does that mean? Uh, we have x and we have y, right? So what is x concatenation of y? What is x concatenation of y? X star y equals to x times, uh, let's say number of digits in y be d plus y, right? Where number of digits in y is d. It's 10 power d. Okay, sorry. So this we can say initially. And then what do we want? Such that x is divisible by x plus y. So what does that mean? X plus y divides x times this plus y. Okay, this thing divides this. If if this thing divides this, if a divides b, a should also divide b minus a, right? Right, because a divides b means a equals b equals to a times k. Means b minus a is also a times k minus 1, right? So you have, I'm trying to simplify this thing into this, because this simplification, why am I doing? Instead of having y on both sides, I'm removing y on some side. Okay, that's some simplification. It's not like a very great simplification, but it's some simplification, right? So that's for that reason I'm just doing that. Okay, for that reason I'm just doing that, and then it becomes 10 power d minus 1. Okay, still d is there. Maybe it's not yet simplified. But then instead of having y on both sides, now I have y on one side, and d is just few possible values, right? There are not much possible values of d. D can take 0, 1 up to so on 9 at max. 9 or 10, 9. So 0, 1 up to so on 9. So I think writing like this is a bit better. Both are equivalent. Both are implies and implies, right? Both are implies and implies. Existence of a d such that y less than or equals to 10 power d. Both are implies and implies. But here we have y on two sides. We cannot say much there. Here we have this. Okay. So now what is it? Instead of this, can we just find something that always works? Something that always works. Like y equals to x. Will it always work? Suppose y equals to x, because it's an easy problem. Let's also look for those things. If y equals to x, if y equals to x, does it work? It's not working, right? Why? Because, wait, what happened? Okay. Hey, his contest is not going on, right? It's finished. Uh, so let's try to make some more small observations, because here we are not getting much, so we should not get stuck there. We should try to make some other small observations. Let's say if y equals to x, will that work? It looks like if y equals to x, this is 2x, but then if we take x common, this is not odd, right? That's not odd. That's odd. That's the only problem we are facing, but it's almost divisible. Do you see that? It's almost divisible. So can we make it y equals to 2x or something like that? If you make y equals to 2x, then this will be some 3x, and then we want that to be divisible by 3. Also, that's not happening that easily, right? But then notice that if it is 3x, if it is 3x, 10 power 9's remainder with 3 is always 1. And then That plus this way is divisible by 3. Y equals to 2x works. Y equals to 2x works. How? 3x divides x times 10 power d plus 2. Why? Reminder with 3. 10 power 9. 10 power d is 3k plus 1, right? So then what this will become? This will become multiple of 3, and then we made it. I was seeing the problem in a more general way, but then okay, if x equals to y itself works, then why not just use it? And then I thought, okay, can we adjust instead of y equals to x, can I make it y equals to some k times x or something where this 10 power d plus k, where k divides 10 power d plus k, that can be a, because we have that on both sides. What about this? Something like this divides x time. So I'm trying to give less importance to this thing now. Then then what does it become? It becomes something like this. Now it just means k plus 1 should divide. We can see this in a general way too, is what I mean. 10 power d plus k kind of thing, right? Like just trying to see that structure, because if something obvious is already satisfying, we need not understand the exact problem, right? We need not understand the problem. We can see it for once, but then if you're not going anywhere, you have to come back. Okay, you should not get stuck here. If you're not going anywhere, you have to come back, like I came back. Okay, because this won't be that difficult, right? B should not be that difficult. So understanding the difficulty of problems is also necessary, because people know B is not the difficult. People who can solve B, they know that B is not the difficult. So they'll come back and then they'll see it. But then if you think B is difficult, then you will keep seeing here, or you will keep thinking something complex. But see this, y equals to 2x works. 3x divides x times this. Am I right? D0 it works, D1 it works, D2 it works, for everything it works. Okay. So now what will I output? And 2x remains in the range too, right? So we solved B. I took some time, but we solved. Let's see how much time I took. Okay, how's that, guys? Someone told proof of this is difficult. What the fuck? I mean, I don't think there is another easy solution. Maybe there is, but if this is the solution of outputting 2x, is this proof difficult? 10 is a multiple of 3k plus 1, 3k plus 1 whole power d, a plus b whole power d, 1 power d will remain, 1 plus 1, 2, 3. Everyone knows 99999 is divisible by 3 plus 1, remainder 1. And then how is this proof difficult? I was trying to see this, I was not able to get anything, and then I was just trying to guess what would work. Because if you notice these things, okay, we have y equals to x may work if 10 power 9 plus 1 is even, and then the problem is done. So just try to fit it like, but that's not happening. But 2x is happening. See? And then we are done. Is this wrong? Is this wrong? I proved it, right? Someone told me my test cases failed, mate. Are you talking to me? Should we follow some rule, like when talking to me, say something kind of thing? Like the video, guys. 31 people out there. Can't you just like the video for the effort I'm doing? Effort I'm putting here. So C is done. B is done. Right? Any comments? Any comments on the problem? And damn, 19 likes all of a sudden. Okay, any comments? Like, what can we say? See, I think, I think, uh, it's important to know the level to know the complex, to know the work needed in B. If you don't know that, maybe I will go further in this, right? If it's a difficult problem, I will go further in this. But before that, if you're not getting anything, if you're not getting anything constructive very easily, then what you should do? If you're not getting anything constructive, then what should you do? You have to step back a bit. But even if you see this too, okay, this is 3 multiple. This is 3 multiple, right? Even if you see this is 3 multiple. Okay, even this is helping. Okay, this is 3 multiple. So can't I just make it like this is what we have to divide now? This is even 9 multiple. Even 8x will work. This is even 9 multiple. 8x will work, 2x will work. So doing this step is not bad. If you think it's entirely guessing, you could have first simplified it little bit and then guess it. And then guess it, because now you have x and then you have some number which you already know. Whatever the d you take, it's either divisible by 9 or 3. Now because you have to make it 9x. If you are given x plus y divisible by 9x, what can y be? Come on, you can try 2x. If it was 3x2, you can try 2x. Right? Done. So this is problem solving, right? Moving from here to here is problem solving, at least. If you think it's about entire guessing. But even if you are trying to guess, okay, sometimes this is become xx can be cancelled out. That's also problem solving. First, let me cancel out x. Let me get x out of the equation to prove that it's divisible for anything. Yeah, so I think I have explained quite good. Already 24 likes. Will the complement of x work? Complement of x in the terms of bitwise representation, right? You mean complement of x? What do you mean by complement of x? You mean it like, mm, I don't think so. Complement in base 10 or base 2? I don't know. But let's go for a bit higher problem, okay? Shibe, don't get disappointed for not solving A, okay? You can solve it because problems can be sometimes tricky. Even uh, it's about realizing how the problems are, okay? You can solve it later. So let me go for D, okay? And then I'll read C. See, you guys should be able to read problems well, okay? Reading problems is like number one. You guys should be effortlessly able to read E, F, or anything. Should not get scared. Read problem, understand the problem for what it is. Maybe you don't know how to solve it, but understand the problem for what it is. This you guys should be able to do very well, because it takes just mental effort, right? It just takes mental effort, and if you are able to do it repeatedly, you will improve in reading problems at least, right? Things are doing work, not getting great ideas. Okay, you're given n segments on a number line. The ith segment is represented by this. Initially all segments are unmarked. Initially all of them are unmarked. Okay, we have n segments on number line. You perform the following operation repeatedly until there are no unmarked segments left. So we do some operation repeatedly, it seems. Okay, in the kth operation, if there are at least two unmarked segments, choose any two unmarked segments, mark both of them, and add a new marked segments xk yk satisfying the following conditions. Xk should be among one thing, yk should be the among the other thing, and xk should be less than or equals to yk. So we mark two things, we add something new. If there is exactly one unmarked segment, mark it. Your task is, so what happens after doing this thing? Number of marked segments will, number of unmarked segments will, number of unmarked segments will decrease by 2. They will keep decreasing by 2 after each operations, right? And then finally if it is 1, we'll just mark it. Your task is to determine the maximum possible sum of lengths of all marked state segments at the end of the process. Now that the length of a segment is r minus l. See, those people are even telling you the length is okay. They mean it's not like r minus l plus 1, okay? They just mean it's r minus l. Does this affect the problem if it is r minus l plus 1 or r minus l? So now it seems a nice problem, right? Because why is it a nice problem? After reading a problem, how you have to view the problem is, you don't, it's not that you have to know a method that gives you the answer of this. It's not that. How you have to view the problem is, you have to form the proof now. You have to form the puzzle. It's like a puzzle and you have to form the proof. You have to form the proof and you have to show that, okay, given these segments, whatever you do, this is the maximum possible sum you can get. You have to show all of that. That's the work you have to do. It's not like you're trying to get do something random and getting something maximum. Okay, you have to prove that that's maximum too. I don't know if I'm making sense or not. To prove that that's maximum, you have to give importance to what you are doing. You have to give importance to problem. You have to give importance to what you are doing. So what can we say? Uh, in one operation, and then we want, after that, what do we want? Maximum possible sum of lengths of all market segments at the end of the process. So finally, everything will be marked. So we want maximum possible sum of lengths. It seems. What do we want? We want to. So how many small observations can be in one operation? Mm, two things, two unmarked become marked, and one more marked will come, or one unmarked becomes marked. These two will happen, right? In the kth operation, what do they mean by kth operation? If there are two unmarked segments, choose. I'm just checking carefully, like should we have to do both of them or we will only do one of them. So and add a new market segment, this thing. So this is a market one. Whatever new we add, it will be a market. We mark two things, we add new thing. Okay. So what's happening? Two things got paid, right? Two things got paid. And then for that pair, we have one market thing. That's an observation because once you pay two things, they will not affect any other operations, right? They are done, they are paid, and then they have their this thing, right? You just paid them. But what do they mean? Taking minimum LI and maximum RJ is always best thing, right? It's always the best thing, right? Taking minimum LI and maximum RJ, that's always the best thing, right? Are people following me? See, sometimes you should not keep thinking, you should not go deeper. What? You have to come and think coolly sometimes because here, after this, I came above and then I thought coolly. I wrote this obvious thing that I can simplification I can do. Don't spoil D for me, okay? What I can think is two segments which are extremes. I mean, see, Ajay, I got it. Before going to greedy, let's write some observations, right? Let's write some obvious observations. What we can say before trying to do something. Let's try to look at the structure of the problem before, okay? Because we need not hurry, right? So now what am I telling is, if you look at the problem, what is happening? Two things are getting paid, and once they are paid, they are good, and once they are paid, they stay together forever. And then you have one more new market thing along with them, but then you only pay unmarked things, right? So it's like the operations are very simple, they are like independent. So what are all possible operations? So first, what you have to do, one simple observation is, what are all possible different possibilities? uh, Once you pair two things, they become unmarked, and also the newly added one is marked. See, the problem is complicated if the newly added one is unmarked, because then the problem is complicated. Why? You are pairing, and then based on that something new came, and then that may get paired with something else, but this is marked. So just this new being marked or unmarked itself may make the problem a lot complicated. But then you guys will see this first letter and then you guys will not even try that, right? Uh, so we have to give importance to problem, because if it is unmarked, then the operation is not that simple, right? But if it is marked, the operation is too simple. You pair two things and then they are done, they are good. So what are all the possible different possibilities? Different pairings. Different pairings or different possibilities now. Okay. And one may be left out. Okay. So let's say there is something left out. Okay. Can I always make it even? Like, can I add some dummy segment is what I'm trying to see for no reason. Okay. I don't think I can do that dummy segment thing. Okay. It changes the problem. So I don't think I can do that dummy segment thing. Now, is this clear that it's just pairings? It's just pairings, because you pair this, you can get again that into that, which is 3 times of 99999 probably. Uh, so here you have to pair this, or something like that. Is this clear till here? It's just a pairing, right? See, it's just a pairing is clear now. Okay, newbies, focus. Don't think D is not for you. Okay, when I am explaining, I'm good at explaining. I like to assume. I like to assume things. So you guys should see. So it's just pairings and maybe one left out. This is what you do. So now it's like a maximum matching kind of thing if you want to complicate, but then probably something greedy may work, or probably something else may work, because it's pairings now, right? Now let's see. Can you find one pair that works? Even if this happens, you can proceed greedily, right? Someone has suggested one pair. If you are sure that pairing these two is always good, then you can proceed. But still, if you pair L1 R1 and L2 R2, what's the answer? It's not minimum of this and maximum of that, right? It's not that. It's choosing one from something and the other from something. Let's say L1 less than or equals to L2 without loss of generality. Then you have then you have two possibilities, right? Let's before going for greedy or anything, let's try to analyze this too, because after pairing, what happens? We have to analyze that, right, to find best pairing. So to find best pairing, so even before this, let's look at let's look at uh, what's the benefit of pairing maximum possible sum of lengths of all things. Yeah, benefit of pairing two things. Okay, see, why am I calling benefit? Because all the segments that are there initially, that's a fixed length, right? So whatever extra comes, whatever the newly marked ones comes, only they matter to us. So now if you see that, what's the answer? L1 is here, L2 is here, and then we have two cases, right? L1 is here, R1 can be here, L2 is here, R2 can be here, or L1 is here, L2 is here, or maybe R1 covers entirely, maybe R2 is here. We have to see, to find the best thing. You have to see you have to understand the structure of this a bit, right? So before going and trying something greedy, you have to see this too. So before someone was trying greedy, before that they have to see what are different possible pairings. You have to go a bit step by step, because you don't want to go in wrong direction, right? If you go in wrong direction, you get stuck there. So you have to do things step by step, like step by step in the sense, like you have to say what you can say first before trying something random, before trying to see something that requires less mental energy than trying to see something's random on here. Okay, so now let's try to see this. Let's try to simplify this a bit more. Okay, let's try to simplify this a bit more. So if L1 is L2, L1 less than L2, let's say R1 is here, or R1 is here is one case, R1 is here is another case, and maybe R1 is here is another case, right? If I just assume L1 less than L2, these are only the three cases possible, right? I'm not even thinking, I'm just working so far, right? I'm just working, trying to write calmly, slowly, what are all the possible cases after you have a pairing. It's just work. It's not like some great ideas. Okay, let's see how it goes. Uh, Here you can choose L1, you can choose R2. So max possible thing R2 minus L1. Here again you can choose R2, again you can choose L1, again R2 minus L1. But here if you choose L1, you cannot choose max possible R1. You can choose R2. Okay? But you don't get the whole thing. You don't get the whole thing. You either choose L1, because if one is inside, the other thing should be inside, right? So one is restricted to be in between this and this. So it's either R1 minus L2 or R2 minus L1. Okay. So it's just always maximum of R1 minus L2, comma, let's keep it absolute 2, okay? What is this here? R2 minus L1 or R1 minus L2. But R1 minus L2 can be negative too sometimes. See here, it's negative. Okay. Or just write all possible things too. Maybe you can see it like this also, right? To write, you can write them like this also. R1 minus L2, R1 minus, sorry, R2 minus L1. Are these the only possibilities? Yeah, just reverse them too, maybe, okay? Because if you're taking max in this, taking minimum in that seems the best, right? I mean, if you're taking, let's say you have two things, because those are all the possibilities. Max in thing, something min in this. Trying to go to max R2 here and then min L1 here, or try to go to max R1 here, min L2 here, right? So, so R1 minus, so it's always just maximum of these two things. That's it, right? Because R2 minus L1, R2 minus L1, R2 minus L1, R1 minus L2. But I'm assuming L1 less than L2. But even if you don't care about that too, it's still, what is it? 1 minute. 1 minute. This assumption is not being used after you come here, right? After you come here, that assumption is not being used anyway. So answer is just this, because we are not using this assumption at all. Even if you replace L2 and L1, it's still the same. Okay. I'm unnecessarily complicating, I guess, but then this is it. So now can you think of a best pair? Now can you think of pairing two things that's always good? Now think of that. Because we have this a bit more clear, right? So now maybe we can think of that now. Maybe that's good. I'm doing good, bro, brother. So let's think for 1 more minute, because if we are proving that this is maximum, we are also showing lower bound. We are also showing upper bound. Okay. When we prove that this is maximum possible sum, you show you cannot get any higher. So let's try to give little bit importance. Okay. As someone already told something like sort by L's or sort by R's, what's the maximum possible you can get by doing these things? Okay, what's the maximum possible you can get by doing these things? it's like finally you have, finally the sum has some ri, some some r's, summation of some r's, right? It's like some r1 r1 plus r2 plus r3 up to so on, minus some L1 finally, because max, if max goes, either of them will come, right? So finally it's something like this, some minus R3 or minus L4 minus L5 or something like that, right? It's something like that. Okay, so now can you say something of the about the whole summation? Finally it's some r's being positive, some else being negative, right? Some r's being positive, some else being negative, right? But the group of else you choose and the group of r's you choose, they cannot be having same things. Like you cannot choose same r1 and same l1 here. Only that you cannot do. Okay, only that you cannot do. So can we always choose smallest else and biggest r's, because that's an upper bound, right? Let's say we have choosing biggest r's and smallest else, but then that may not be possible if something is in the half of smallest else and also in the half of biggest r's, then we cannot take that. Then we cannot take that in both, right? So let me see for some more time. Okay, what I'm trying to see is I'm trying to find upper bounds, because what is an upper bound? And take max hours, biggest half hours, and smallest half else. This is an upper bound, right? I mean, this is definitely not a possible pairing. That's where upper bounds are entirely different from what you try. I am wantedly not looking at pairings. I'm wantedly trying to look at upper bounds, because I want to show you people how are upper bounds useful. Because if you're proving what an upper bound means answer less than or equals to this is an upper bound. And then we find better upper bounds. When we find better upper bounds, we come to optimal, right? If you find the strongest upper bound, that's the optimal. Because if you are proving this is optimal, you're also showing opt plus 1 is not possible. Okay, so now this is an upper bound, but then, so if this is an upper bound, that also says in all the cases where you can choose top halves and these things, let's say if smallest else and biggest r's doesn't uh, doesn't coincide, if they don't coincide, then it's done. Okay, then it's done, because that's the answer. But now what if they coincide? What if something is in both biggest or and smallest half? What if it is like that? Then you cannot take that value in both. Okay, you cannot take that value in both, but at least you will take it in one value, I think. At least you will take it here or there. Okay, you cannot take that in both, but then maybe at least you'll take it here. So let's see again. Okay, so I know the way I am solving seems entirely different, right? I'm not even looking at test cases. I'm not looking at to see what's optimal. I am purely looking for upper bounds. That seems a bit weird. I hope viewers are there, because I can prove my point by that. Okay. See, with upper bound itself, with this upper bound itself, I have all the cases where if first halves, first L halves, and next R halves, highest R's and lowest L's, If they are like disjoint, then I have my answer. Right? I mean, then this is the answer. I mean, if they don't coincide, then that's the answer. It is tight when they don't coincide. Means, okay. Let me draw here too. What do I mean? So you're looking at else. Okay, you're looking at else. These are the smallest else, smallest half of else. Okay, and then you're looking at biggest R. Okay, but then the answer, if the L of this and the R of this are not coinciding, means for this you have an L here, maybe you have an L here, maybe you have, sorry, you have an L here, you have an L here, or you have an L here, or something like that, then that's the answer. Means if they are entirely divided, if they are entirely separated, then that's the answer. Okay, entirely separated means these first L things, maybe L can come here, but then it's not coming in the first half of L else. Then the answer is this. But what if something comes to? What if few things are coming in the first half and the last or both? If few things are coming in the first half, first L and the last or both, then what can you say? Then 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 let's try to see if you can say making it R or L, which is beneficial. Can we say that? Can I say even after this, the values are the values are some else, okay, some else, some R's. But then whenever there is an edge from here to here, we don't take both. We only take one. In this way, you have this, this, some min else and some max R's. But maybe this can be close. I think I should try in a better way. I don't know. Time is slipping up. Right? Yeah, if you can't understand, just try. Okay. See, upper bound means answer is definitely less than this value, right? Because if you remove max here, it's just some R minus some L. So answer, if you remove max and then try to find an upper bound, means taking the best possible R's and taking the least possible L's, answer should be less than or equals to this, right? So let me look at this one more time. Okay, give me some time. I'm guessing something. Maybe this much is not needed. Maybe some observation simplifies the problem. Maybe this also would work. Some best pair also would work. But let me try for some more time. Maybe we can brute force too. Okay, maybe we can brute force too. Now, maybe we can brute force on the highest L. Maybe we can brute force on highest L and then solve the problem. Okay, see, we are taking half else, right? What if I brute force that? Can that help? Would that help me? Uh, because the thing is, when it is like this, we have to go this side of else also, right? A bit of that side of else also, right? So let's say, so now I am coming back to sorting else, and then trying to brute force them a bit. Sorting else, sorting else, and then brute forcing that. Okay, sorting else, and then brute forcing that. These else will be paid with, these else will be paid with, some of them will not be paid. Okay, some of them will not be paid, but some of them will not be paid. But if you brute force, and then it's like, if the length is half, okay, if you're just looking at where you must pick it. So if you have this thing, what can we say? What am I even doing? I want to verify well. 1 minute, or give me some time. I want to verify well if this length can be brute forced or so. Means trying to take half things from here. Let's say you're taking half things from, sorted in terms of L order, trying to take half things from here. Okay, that happens at some point, right? Okay, you're taking half things from, you're taking these L's, you're not taking this R. Sorry, you're not taking this L. Means you're probably taking the R because, wait, I still don't get it. I have to see this properly, I guess. I have to see this a bit properly. So it's always max. Okay, it's always like max minus this. But then here it's like, okay, here it's like either this or this. Is the stream ruined? Should I go for C? Let me give some more time, guys. We can solve this. We can solve this, let's say. What's the best pairing? Can you say something greedy? Can you say something greedy about this? Let's just look at smallest R and biggest L. Okay. What am I doing? Give me one more time, one more minute. Give me one more time. I'm going somewhere. We are going somewhere. Give me some more time. I feel weird. Not weird. I don't know if this is a good way. I don't know if approaching the problem like this is even good. So now I have an idea. What's my idea? What's my idea? The same one as before. Okay. I know the problem is not this difficult, but then I don't know why I'm applying this idea. Let's draw a line here. This is half of L by 2. In terms of L sorted, this is half. And then we have in terms of R. In terms of R's, this is half. So we have half highest R's here, half highest least L's here. I'm using the same thing. 1 minute, but then I got something now. Maybe I'm complexing, but then let's see. Why am I complexing? Because I'm looking the problem as a whole. But if you fix something on brute force, maybe the problem is simpler. But then I'm looking it as a whole. If I'm looking it as a whole, so now these are like half things are here, right? Half things are here. I mean, floor of half things are here. Floor of half things are here. Okay. But the problem is some may be the same thing. But then if you have something as same, you have something here inside. Okay. So the number of things you have here, the other things are pairing here. Okay. The other things are getting paired here. So finally what do you do? Finally what do you do? So for everything, I'm trying to see what an upper bound. For everything that is here and then not here, I'm taking them already because they can be taken, right? Let's say we are taking all of them. We're taking all of those things that are not here. Okay, that's the best we can do. Now we have this thing, these things, and now we have these things. Okay. Now we have these things and now we have these things. But now the problem is the other things are the best you can do in some way because we have seen that before too. Now, if you take few things here, if you take like jet things here, if you are taking jet things here, you will probably take uh, k minus jet things here, and then for these jet things, wait a minute, wait a minute, wait. Is it simple? If you have one here, if you have another thing here, still you can take these things. Still you can take these things because you pair this shit with this shit. Wait a minute. I should give up. But I'm seeing if there are two things, if there are two things, can that be taken? If there are two things, so 1 minute. What I'm trying to see is, can, if you have two things, what does that mean? If you pair this with something else, even then one of them is missed, right? If you're pairing this with this, even then one of them is missed because you only get this one and you only get this one. You don't get both of them into consideration because I'm just trying to see if I pair this and this, can I try to maintain all the values? No, I cannot maintain all the values. Still, the values will be lost because when you include this itself, the values will be lost, right? So now it is like you choose few things from here and then the remaining k minus z things from here, and then you choose k minus z smaller things from here, and then you choose z things from here. So now it is like, all these smaller values, these things are definitely bigger than this, right? Why? Because these L's are greater. The L's itself are greater. That means these odds are definitely greater than this. For these things, these L's are definitely lesser than this. So now, to choose some things from here, and some things from here, and some things from here, and the remaining things from here, and the remaining things from here, seems somehow simpler, right? This is what I was thinking a bit. See, I am looking the problem from a whole. That's why it's looking a bit complicated. But then you could have very well maybe brute forced number of things here by fixing number of L. By fixing L itself, you could have done that. What I mean is by fixing just L itself, maybe we can solve the problem without observing this thing, without observing this niceness of the problem. I mean, I don't think it's nice. It's unnecessary to do these things, right? It's unnecessary to be this much mathematical in the problem and say these are first half. Let's see for one more time. So now you take few things here and few things here, and remaining things here and remaining things here, and then it works. You need not even worry. Now you have few smaller things here, few equal number of bigger things here, and few smaller things here and few bigger things here. Now you have to take. Now you can take 1 minute for things you take here. So we have to be careful. Let's say you pair something here with something here. Okay. Instead of that, if you pair that with, then two things will be paired here too, right? If you pair something from this side to this side, something will be paired here too because that also will exist because you have to get all number of pairings, right? But then instead of doing that, if you do this and this, the answer doesn't change. Am I right? Why the answer doesn't change? Because you're able to take this as minus L, you're able to take this as plus L, and then you're again able to take the minimum here and the maximum here. Okay, so pairing, I think that's the way. I think, I mean, that's the greediness. So you have to see for the remaining things, because it's not just these two or one pair, but then the question that I'm doing now is, can I pair something from here to some or from here, some different or, not the same or? Then there will be something from here to something from here too. But then you need not do that. You can just do this, you can just do that instead. I think still you will have the same value, because this length plus this length, I mean, the advantage here is they're getting simpler here, right? They're getting simpler. You can always choose the minimum and this as the maximum, because see, now you have two things here, they are getting paid. And then whatever this and whatever this is, they are getting paid. Okay. Okay, so what am I trying to say is, instead of pairing these two, you could have just paired this and this and this and this, and then you will have a better value for sure. So this full complexity just says that you can always pair. The whole complexity just says that in terms of L, in terms of L, you pair these L things. Everything will get paired, right? You pair these L things. Guys, I have to just leave this. I have to go for C because I cannot keep taking time. Guys, let me go back to C and then I'll come back to D. Okay. Let me go back to C and even. I'll come back to D. Okay. We have done something. Okay. We have done something. Maybe we need not complex this much. Let me come back. Uh, Let me read even. Okay. We can come back. I don't want to waste stream. Okay. I will definitely come back. We'll try to see this idea a bit more. Okay. It's not my approach. I'm just trying to use some things here, okay? Because everything will get paid to something, right? Let's assume it's even number of things. Everything will get paid to something. So what I mean is, maybe I'm not looking two things right. Maybe I'm not looking two and things. Maybe I'm not doing things right. I am very sure we need not think this complex. I'm very sure about that. But I wanted to unnecessarily see if it works. That's it. So let me go to even and then come back. Okay. I have unnecessarily complicated that. I'm sorry for that. A valid configuration is defined as an arrangement of n piles of stones such that the number of stones in each pile is an integer between 1 and m. So if number of stones in each pile is this, that's a valid configuration. Okay. I think I should make some obvious statement rather than this. I think I should make some obvious statement rather than all of this thing. What obvious statement can we make? Uh, what obvious statement can we make? Probably like trying to say something like pairing these two is better than pairing things like this and this is better than pairing things like this and this. That's what we will probably say, and then we know pairing what is good for us, and then we will do proceed greedily. Mostly that's the case. But then I don't know why I'm complexing, because I am assuming for this taking this is itself is better rather than going or taking something else. So I think this is complex because there are many things here. So let's just skip that. Let's just keep it aside. Okay, let me try even. It happens in streams, not in streams. Even in contests, I face this problem. I guess. Given a valid configuration of n piles of stones, some indices from 1 to n are marked as good. So we have valid means Everything being in one and m. Okay, I should have just paused. I guess I should not have gone further. All being in between 1 comma m. I definitely complexed it. It's not proving that would not be that difficult. But then I got one thing and then I tried going in that direction unnecessarily. Okay, maybe some greedy will work. Given a valid configuration of n piles of stones, some indices from 1 to n are marked as good. Alex and Bob start playing. I mean, why it went messed up is I'm not considering two things. I'm only considering one thing a lot. And then these things also come here and then it's a bit messed up. It's not getting simplified. I thought here I can use some concrete logic, but then I was not able to use it. So I'm coming back to even. Let's try to solve it later. Given a valid configuration of piles of stones, it's still fine. Sometimes trying to use some logic is good for you. Okay. The number of stones given a valid configuration of n piles, some indices of from 1 to n are good. Alice and Bob start playing a game, taking n minus 1 alternatively. So this one we have to try a bit. Okay. In each turn, they have to perform the following operation. Some are marked good and they have to perform the following operation. Since choose an integer I such that I less than or equals to p, p is the number of piles left. If I is good, remove the ith pile completely. Note that after performing the operation, once the number of piles decreases by 1 and the remaining. Okay, okay. The game will end when there is only one pile left. It is guaranteed that the index 1 is always good. Okay, let x denote the number of stones in the final remaining pile. Alice wants to maximize it. So some indices are good, and then when they come down, again, what good is redefined. Okay, you guys get the problem? Did you guys understood the problem? I mean, knowing solution is not that beneficial, right? So C or even is same. Let's try even. Let's try even. Okay. Let's try to give our best. Should be easy. I can't even say 600 solves should be easy for me, right? Choose an integer, any integer I such that is I is good, and remove the ith pile completely. So we know some indices are good, and then after you remove that, things will fall forward, and then again you know what are good things. Okay, you can only remove good things. So it is like, let me take it here. It is like you have these indices, good, uh, bad, good. You have some bads, you have some goods. Okay, you have some goods, you have some bads. Okay, up to so on it goes. And now what happens? There are values here. When someone removes this value, everything in the later will come forward. That's what reindexing means, right? So people can keep plucking values from here and here and here, and then things keep coming forward and forward. And then finally, one thing is left. This is the question, right? So at each step, they can remove from some good greens. They can remove from some good greens, and then things later will fall forward. Okay, and then things later will fall forward. Now let's read the whole problem. Problem is a bit understood, right? Redefining of good in the sense, indices will be redefined. So this is what I mean, like reindexed. Sorry, not redefined. Like a remaining pulse are reindexed. So reindexed means they just come forward. So now Let x denote the number of stones in the final remaining pile. Alex want to maximize x where Bob wants to minimize it. Both Alex and Bob play optimally. Find the sum of x over all possible valid configurations over modulo n. So what's the first step now? Simplify the game. Okay. And then count it. So simple. It has two steps. If you are solving C1 even, you're probably solving these two steps, and then you have to do optimization for E2 probably. Okay. So the game will end only when there is only one pile left. Okay, so now we have to solve the problem. Given there are these good things, you have to say you have to say sum of 2 power n over all test cases does not exceed 2 power 20. Okay, this seems scary, right? Because we have to do something 2 power n. But before getting scared of this, we have to solve the problem. We have to solve the problem logically, right? Given that you have all the computation power, you have to solve the problem logically. Maybe you can use some subsets also in your solving, but then you have to solve the problem logically. I mean, what I mean is you have more power in solving the problem. You need not restrict yourself. So now let's solve the problem. For for okay, let's say maximum. Who wants to maximize? Who wants to minimize? See, now what we have to look for is, again, we have to look for like lower bounds or upper bounds. Lower bounds or upper bounds means if you can say whatever happens, Bob can maintain this. Then whatever happens, Bob can maintain something. Then answer is at least less than or equals to that, right? And whatever happens, Alice can maintain some value, let's say some big value. Then so one is always not there, right? Because one is always not there, what can Bob always, okay, who wants to minimize and who wants to maximize? I mean, it's same. Minimum or maximum is same from both the directions because those are just values. Okay, the what 1 less than or equals to m less than or equals to 2 is this version. And so let's solve easy version. Now we only have two things, m and 2. Okay, I think that's why it's good. Now we only have two things, right? And then m can be till 10 power 6. So even is m is 1. Do this in many problems. You guys should see, okay, what if values are just 0 1? What if values are just 1 comma 2? Can I solve them? You guys have to do that because this may have the core logic. This may have the core logic, right? In normal problems, you can split them into two problems, right? Sometimes based on constraints. Because now, even I was doing that. Because why was I doing? There is something small, there is something big, let's say. Can can Alice maintain this big value? Is the question, right? Can Bob maintain this big small value? Is the question, right? So whatever Alice do, if can Bob maintain some one, then answer is one. I was trying to look for the same similar thing, whatever even is. Okay. So now we have to think the array has only ones and twos. So this will make, given this configuration, there are some things that Bob can always protect. I think there are some things that Bob can always protect, I guess. Right? Let's say this is the index. If Alice wants to remove that index, no, it's not just like that. It's not just like that. Bob can always maintain this. 1 minute, let me think. Bob can always maintain this or something bigger, is the thing. Bob can always maintain this or something smaller. We need such an index. Okay. So let's just think generally. We have some twos, we have some ones. Is there a way to always make some two stay finally? We have to think for that. Okay. Maybe we can see some special configurations too. Let's say there is only one green. If there is only one green, if there is only one green, lost value, Bob can at least maintain this thing, right? Because whatever people remove, only this will remain finally. So answer is that whatever they remove, answer is that lost value would be the answer. If there is only one green, let's try some more time, guys. You also take pen and paper and try the problem because solving post-conscious discussion are all same things, right? Try the problem a bit. So if you have one more green here, okay, if you have one more green here, Alice, Alice can save something. The first player can remove this, and then they can bring this before this, right? And then they can bring this before that, right? Once they bring that thing before that, then this also cannot be removed that easily. After that, now we have two kinds of things. You either remove that or you either remove this. And then it keeps reducing. But then again, whenever you remove this, one thing will come this side. Let's try some more time. Let's try to think. Let's try to say something. How to solve the easy version? How to solve the easy version with just one and two? Try, guys. Sometime let's try. Guys, take pen and paper. Try. So if you remove a green, then after reds, no, they are not getting swapped. The thing is, values are coming forward. Let me confirm that with a test case. Okay. So yeah, remove that and then one will be left. Remove that and then two will be left. Remove that and one will be left. Remove that and then two will be left. In the second test case, the final pile is always one. It seems. Subsets also, right? So let's think in that direction too a bit. Okay. Can use subsets also. Can we use subsets and then say something? What happens after one operation? If only one green. So let's try to understand the structure of the problem. Okay. Not getting anything. Is it because of low sleep? I haven't slept yesterday at all. Easy version at least. Okay, this is simple. Can Bob remove all twos? Can Bob remove all twos? Can Alice remove all ones? Whatever happens. So this is the question, right? Because okay, at each time, and sometimes they may have to remove that too. Sometimes they may have to remove that too. Okay, you have ones, you have twos. Okay, you have ones, you have twos. All of them will go to some hole. All of them will go to some hole. Why am I not able to guess at least, right? And then see, this should be simple. This should be a simple guess. When is it possible to take, and when it is not possible to take? N is just 20. Okay. We can also say this thing. Okay. What can we say? We can, if you have a green, if you have a, all the things come here. If you have a green, and then all are like yay, 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 then all of them will be removed. Wait, what am I saying? So you have twos, you have ones. So so Alice tries removing ones. Bob tries removing twos. Right. Sometimes they are forced to remove what they want to. Okay, when are they forced to remove what they want? When are they forced to remove what they want? Let's take Alice. All green have two. Then Alice must remove two. Right. We can even do work. What work can we do? If when losing, okay, when losing, what's the losing position? So when losing, when will someone lose? When will someone lose? If opposite guy removes your thing, you lose, right? Means what is the losing position? What is the losing position? You have your value on green, let's say. All of them are twos, and there is only one. Sorry, all of them are ones. And then there is only one, two, and it is on green. This is a losing position. If Bob plays, like if Alice goes here, then Alice loses. Means if Alice comes here, Alice came here such that all or one, but then two is on green. If allies make such a thing, allies will lose. Okay. So to not make this, what will allies do? To not make this, what will allies do? Allies can. So whatever allies do, it comes here. Okay, whatever allies do, the two comes here. Let's say that's a losing, right? Because Bob comes and then Bob removes this two, and then it's all ones. So I think if allies does this, we're trying to see the last move where allies loses. Okay, if there are two twos, allies can try to maintain just two twos by removing some other thing. Let's say if this is also two and this is also two, then allies can mm, remove this thing and then this will be saved. Okay, but then I got likes by mistake, I guess. People should just unlike this stream. Guys, I'm tired. I'm ending the stream. I will solve at least this. I will solve D2. Let's try a bit. Because we have to count that two later. So it should not be that difficult. We have to find one observation at least. We have to find at least one observation, okay? After you remove that thing, what happens? After you remove one thing, what happens? Other things will come forward. After you remove something, things will come forward, right? So what have happened? See, we need something that allies can always maintain, okay? So if allies is winning in games, how it will be? Allies did something, Bob can again come back into the same configuration. And then allies did something, again Bob can come back to same configuration. That's what we want, right? So when can Bob win? When can Bob win? When can Bob win? If only 1 2 is there and it is on green, Bob wins. So whatever allies do, when can 1 2 be on green? Whatever allies do, when can one green be on green? If what happens after one operation? See, it's all about trying to see what happens after one operation, okay? Mostly it's about that. After one operation, let's say there is only 1 2. So uh, two two twos are there. Okay, 2 comma 2 is there. After allies does something, it becomes, what are losing positions for allies? It becomes 2 on green. 2 comma 2, only 1 2 is there. After allies does something, it becomes 2 on green. Okay, this is another thing. So for this to happen, what are all the possible configurations? See, we are trying now. My idea approach is try to find some configurations where allies wins and then try to generalize them. Okay, try to find some basic configurations where allies will definitely lose and then generalize them. Its game is a bit symmetric for both, right? Game is a bit symmetric for both. Symmetric means there are some losing positions and winning positions, and once you see the structure of the final structure mostly will become, in these cases allies will win and whatever allies do, it will become to some other case and then Bob can bring it back to this case and then again whatever allies do, it goes outside and then Bob can bring it back. So that's how it is. So we have to understand what happens in one operation. That's one way how to understand what happens in one operation. What happens in one operation? Something will be removed from this, everything else will come forward. One is always good. Wait, wait. Is the answer okay? Answer is whatever crosses second hole. Answer is whatever crosses second hole. Answer is whatever finally crosses second hole is the answer. So if Bob is winning, he can always make one cross the second hole finally. I'm really sleepy. It's not being that simple somehow. I thought halfway I thought these videos of yours are really boring or really shitty or something like that. I'm not able to solve Pradeep. Wait, we didn't even solve two problems so far. Guys, I will go get some water. Maybe then I can solve the problem, okay? Please wait for me. Am I back? So I really went for water, and then I thought, okay, I will once look at the problem. Okay, I thought I will once look at the problem. Yeah, I thought I will once look at the problem. But then I realized, okay, if it is 2 power m is allowed, all possible configurations are allowed, right? I'm good, symmetry. I think I'm going mad. I'm just joking. So, see, guys, I wasted a lot of time. 44 minutes I wasted on even unnecessarily. It is we can brute force all possible configurations, okay? And now, see, when something is brute force, and then you think apply logic, you get nowhere. And because of this reason itself, many people try so hard on some problem, and just because they can't solve it, they think their thinking capacity is not that much. Just because of this fucking thing. We have to learn how to brute force, I guess. Okay, so now if we know answers of all, okay, if you know answers of all things, all sequences of length n minus 1, can you find answer of all of any sequence of length n? So this is the question, right? You know answers of all sequences of length n minus 1. Now can you find answer of length n? So now it comes, okay? What are possibilities for first player? See, because the game is symmetric, we can maintain just one state. We can just maintain one state. First player winning or losing. We can just maintain this. Why? Because if you maintain this, that's probably enough. Because after one move, now the other guy is first player, and then the sub-array has been changed to complement or something like that, right? Okay, where are we? It's not drink more water. I'm trying to think without thinking from high level, right? Because it's obvious 2 power m. I'm not getting anything. All possible configurations itself for 2 power n, right? If m is less than or equals to 1. So I'm trying to explain nice things now. Okay, I'm trying to explain nice things. Focus here, guys. So the question is, now now we will use little bit of game theory, brute forcing game theory. Okay, so let's say we have winning configurations and losing configurations. Okay, of first player has at max n possibilities of his moves, right? And if if at least one of this is losing means losing for second player, then he wins, else he loses. So this is the game, right? That's it. So after we have choices for doing one move, and after that you have n possible configurations. Among them, if at least one is losing for next player, then first player wins because he will choose that and then he lose. The next player will lose. Okay, is this clear, guys? Is this brute force clear? I haven't slept, bro. Like I haven't slept, guys. For yesterday, I haven't slept at all because when I don't sleep, I don't even exercise. So I think is it clear for most people? Not at all. I slept little bit. I slept at 6 and then I have to wake up for work, right? I slept at 7 and then I woke up at 11, I guess. Not that bad. 8, 9, 10, 11. 4 hours. Mm, I don't want to do this. I want to sleep well. I never do this. This happened by mistake today because there's a lot of pressure from work, a lot of pressure from other things, a lot of pressure from CP, a lot of pressure from contests. I'm just joking. Guys, is this clear? Is even clear? Please say. I need more people. Say even, is it clear? Like, is the recursion clear or should I explain it a bit more? So we have possibilities for first player and possibilities at max. So after you do this, okay. So now we understood the game theory part, right? So with using this logic, you can find states for everything. But if even is about finding states, E2 you must use the same thing, right? If even is about finding states, E2 you cannot escape this now. You cannot escape this because 2 power m is there in E2 too. You cannot escape this. Now you have values till m. Okay. Now combinatorics part comes. Probably. Because in even case, you can already brute force everything. You just go over all possible things one by one and check if it is winning or losing, and then it's done. But in E2, when you come to E2, okay, now when you come to E2, so when will X be the answer? When will X be the answer? Is it easy to compute? Or when will greater than or equals to X be the answer? Is it easy to compute? Tell me this, guys. Among all possibilities, say water. I solve this instantly again. E2 is solved instantly again. Do you guys see the thing? This may not be that easy to compute, but this is easy to compute, right? You can choose the subset. You can So this is easy to compute probably because greater than or equals to x, number of configurations in which greater than or equals to x is the answer for allies because he's maximizing it, right? This is easy to compute. Now what will you do is nothing but number of configurations where you'll make all of them as 2. Let's assume you're making all of them as 2 and remaining things as 1, and now you have it. Okay, this is easy to compute, right? This is easier to compute, right? So you do is solved, guys. You do is solved. Do you get that? See, for E2, I have used my problem solving abilities that, okay, if even has this subset complexity, we cannot escape that for E2, is what I have used because we cannot escape that because we must do that. See, we will try to see it in terms of this, right? So, so let's take some configuration. Let some subset be greater than or equals to x values. Okay, so let's mark greater than or equals to x as 2, less than x as 1. Okay, now you have two sets some places, you have one at some places. Now your previous even answers you how many subsets, are winning, how many subsets are winning means in how many subsets you can maintain 2, means in how many subsets you can maintain, answer is you can get, in how many subsets allies can get greater than or equals to 2, right? You can probably compute this. Okay, to add combinatorics part, let's fix number of greater than or equals to x things too. Let's say you have z greater than or equals to x things. Okay, in how many ways? Okay, I'm fixing that. I'm not even fixing because only the count matters, right? Only the count matters because you will place them anywhere, not just the count. uh, so okay, now I mean I'm trying to get the how many subsets with greater than or equals to 2, right? Because we have m being big, n being big, both are big. You cannot do 2 power n into 2 power m, so you cannot go over each subset. You cannot do for each subset for each. 1 minute. Yeah, because m is big. Once you fix x, you cannot again go over each subset. That's why I'm trying to fix length. Okay, I'm trying to fix length because you cannot do 2 power n into 2 power into m, right? So I'm trying to fix them by length, and that's the best combinatoric part you can do. Do you guys see how it is solved? See, no, see. Now, uh, answer this. Can you answer if greater than or equals to x is possible or not? Given a configuration. Answer this. Given a configuration, can you answer if greater than or equals to x is possible or not? You make all of them as 2. You make remaining things as 1. And then you see the events database. I can't use database thing. And then you see the events thing. And then you can see the events thing if 2 is possible. Right? So, so this means you can probably compute these two. And number of ways you can have So number of ways you can have greater than or equals to x things at some specific places is known. If you know some specific places, so let's say you know these positions will have greater than or equals to x. Okay, let's say you know these positions will have greater than or equals to x. What is the number of ways you can keep greater than or equals to x there? X to m, and remaining things will have less than x. Then you will keep x minus 1 times. This product is nothing but this product is nothing but if you have z greater than or equals to x things. Okay, this product is, what is this product? If you have z greater than or equals to x thing, this is m minus x plus 1 power uh, m minus x plus 1 power z times x minus 1 power n minus z. That's it, right? If a subsequence has z has z greater than or equals to x things, okay, this is fixed value. Now we just have to, this is just the weight, number of different configurations is just this. I mean, these many things will map to one, these many things will map to one 2112 thing. Is this clear? I think I explained better now. These many things will map to, these many things in 1 comma m things will map to this thing. If you are looking at, it's being a bit complex, but then what I was trying to say is, if you have these answers, if you do answer of greater than or equals to x, number of things, answer is greater than or equals to x minus number of things, you have answer of equals to x. So in this way we can compute this for everything. Okay, is this being clear? So we can do E2. A bit clear, right? So what are we trying to do? We have fixed, we are looking at, yeah, we are looking at, so let me be clear again. We are looking at greater than or equals to x things. Okay, x things that will win. We are looking at, we are looking at configurations where greater than or equals to x things win. First, this is the step. And once you are looking at that, you know, answers of this can be just x2's, sorry, this can be mapped to few ones comma 2, 1 comma 2. So you will just make these things as 2, these things as 1. Then you can know how many things that will win. But how many configurations will map to one such thing? How many configurations will map to one such thing? Is all one should have, all one should have 1 to x minus 1. How many ones are there? N minus z ones are there. If you fix z, the length, if you fix z, the length of number of twos, then number of configurations that are mapped to one thing will be fixed. And once you know number of configurations that are mapped to one thing, if I write it clear, so configuration gets mapped to its binary string. Okay, configuration will get mapped to binary string. Okay, this is an order pair, let's say. And then we want number of winning binary strings. So we want number of configurations where this is winning. We want that. We are looking at this. So instead of this, what I will do, I will fix one binary string. Once you fix binary string, I'm trying to see number of configurations it has. That depends on the length of the binary string. Okay, that depends on some, that's a function of length of the binary string. Okay, now what I want, now I cannot go over each binary string again because I'm going over x already. I cannot go over each binary string. So but this value is fixed by uh, this value is fixed by z, right? So I have only f of 1, few things has f of 1 times binary strings with 1 1, f of 2 times, so it is f of z times f of z times f of z times binary string. So now these configurations are removed. So it's nothing but, if you remove the configuration, it's nothing but f of z times binary strings. Okay, if you remove the config, because now we have to see how many binary strings will work. Summation over z. Okay, we are just counting these things where this is a configuration and this is a valid thing. So sometimes it's 1, sometimes it's 0. We have to count number of times it's 1. So what we have done, we have, whenever this is common, I'm first fixing that. Then it's just nothing but same values coming over and over again. How many times will come if you fix binary string length be z? If you fix that length to be z, then it is summation of over different z's. This thing will come f of z times. Now again binary string of length z. Now we have to see, if binary string is 1, this weight will be added. If the binary string is failing, this length will not be added. So what you need is number of binary strings with length equals to z, which are correct. You just found this value. Then you just compute f of z times that value, and over how many different z's are there? Z is from 1 to 20, and then you have your answer for where x greater than or equals to z. And what is f of z? This is f of z. Is this explanation better? Is this explanation better? And then it's very famous technique that if you have greater than or equals to x, comma greater than or equals to x plus 1, it's not a famous technique, it's a good technique. If you have greater than or equals to 1, greater than or equals to x plus 1, you have number of things, it is x, means number of configurations where answer is greater than or equals to x you have. Number of configurations where answer is greater than or equals to x plus 1 you have, means you have number of configurations where answer is x because you subtract those two. Okay, it's not standardized, it's some good problem. I mean, that thing is a bit known. uh, if you solve some combinatorics problems, it's not that easy standard. But then you can use this problem itself. Okay, in this problem this is being easy to compute, that's being obviously easy to compute, because 1 comma 2 means this only, right? Now you have to think, okay, this problem is obviously this thing. How can I get number of x things? Because if you have number of x things, you're done, right? So we have to implement even and e2. Okay, I can do that effortlessly. Why? Once you have even, e2 is too simple. E2 is, you have f of z. You just have to count for each length of binary z strings, number of ones, number of winning things, you just have to count that. And then it's just this small summation. See, if you make implementations clear, if you make things clear, I was able to see this on top of my head, but then you guys can write slowly. Okay, configuration, comma, binary string. I want number of counts of this thing being 1, this thing being winning. But before simplifying that, because for each binary string itself, this is fixed value, which is f of z depends on the length of the string. So how many things I have? Summation over z, f of z things I have where binary string of length is this. And now if I maintain this value quickly, because I cannot do 2 power n times m, if I have this value maintained for each z, only length is becoming, see, after fixing ones and twos, number of things that map to one binary string, that is depending only on length, is easy to see. Because now you have to come from configurations to binary string, means twos are fixed, greater than or x thing should go there. Number of configurations, that number is repeating, right? That's why I went to length, because length is controlling that number. So that's not intuitively, it's not intuitively, you can easily see that. And also the fact that you cannot do 2 power n times here. Yeah, also by also that fact. Okay, we have even and e2. Done. See, I didn't get scared of e2 after solving even, because I am good at combinatorics. So now it's time to flex my implementation skills, right? Let's go for even. Let's fix dp of n of some mask equals to, what's the answer? Dp of n of mask, you have to look at masks of n minus 1. Let's just have these things. Okay, now you have to look at dp of n of mask minus 1. Okay, uh flip it. Where you have to find all these values. New masks equals to, new masks equals to, remove one thing, whatever you get. So this is easy. You remove one thing, whatever you get. This is easy. Computing new mask is easy. Why am I flipping? Because the guy has been changed, right? The opponent has been changed, right? So for him, ones or twos, twos or ones. That's why I'm just flipping and then I'm just finding the answer. Okay. Is that clear? It's also using the fact that it's symmetric. Otherwise, you try to do two operations. That's not needed. You can brute force one operation. That's enough because it's symmetric, right? Lag. What is smart idea though? But then okay, yeah, yeah, that's a bit smart idea, little bit. But then that we can see obviously from 1 comma 2 that is being symmetric. But then you guys see how the bigger problem is being solved by easier versions that well. Bigger problem seems untouchable, but then you have to think. Let's say some easier version is not given. How would you solve bigger one? Maybe you will try to compute, is this solvable? Because it's 2 power n is small, maybe you go for subsets. For subsets you will try to think this is easy to compute, so it's again solvable. It's not that difficult, because even I came to in the beginning itself, I came to greater than or equals to x is possible or not, we can see, right? I came to that before seeing even itself, I was able to tell that. So I think e2 is not too hard in that way. So it's a bit direct problem. I complex things because I was trying to see something nice when there is nothing nice in that. Okay, a problem doesn't have anything nice, and then I was trying to see something nice. How can I see, like, even if I use something, so all of my techniques. So we will implement this now. Okay, let's just try to implement this in n comma m scene n scene m. M can be one, it seems. Now this one's, now this one sits here and whispers things to me. Now I have the devil inside. This one made it big of me. I'll go to washroom and come. Do you have viewers? So guys, let's try that. Okay, let's try this. And then we have to take input of C of n, right? Let's try to just do zero based index. It works. We know what where holes exist. Okay, we know where holes exist. Now in dp of n of n means only first thing has been considered. Only first thing is there. Only two things are there. So this is enough for us, right? And what does this say? Given n things and you have the subset of twos, let's focus on subset of twos, can allies win? Okay. Now what is dp of 0? There is only one element. After this, if m equals to 1, what are all the possible configurations we have? We have all ones, only one possible configuration, and the answer is 1. I'll just eliminate that unnecessary case, okay? dp of, for what is answer? dp of 0 of, when there is one thing, if it is 2, you're winning. dp of 1 is 1. dp of 0, I'll just initialize it to 0, okay? We anyway only see, I need not initialize it to 0, okay? We anyway see, our assumption is will be computed for all 1 power I masks is our assumption, okay? It will be computed for all 1 power I masks is our assumption, okay? This world is primal. So for 1 power I plus 1 masks. For this, if we write it for 0, what's the answer? What's the answer? 0 is losing. For 1, what's the answer? 1. We are winning. Alice is winning. Okay, from int I equals to 1, length, let's say, length equals to 1, L less than or equals to L less than N, L plus plus, not length because I works, because we have two things, right? Okay, now we go for all masks. Int mask equals to 0, mask less than 1 less than or equals to I plus 1, because my assumption is I am computing everything for these bits, right? Our assumption is we compute this for everything. Mask plus plus. Now what should we do? This wall is Brahma, my grand angel. Now what should we do? We have various possible answers, right? We have various possible answers. What are those various possible answers? We have mask remove whenever c of I is 1, c of j is 1. We just have to remove this bit. Whenever this 1, you can remove that. These are all the possible things we have, right? How do you compute that? You have this. Whenever c of j is 1, you have to remove that. Means maybe just take reminder with that. Okay. Maybe take reminder with that and then maybe shift other things by more than that. Okay. So vector int pos, let's say what are all the possible values of the next thing. For int j equals to 0, j less than uh, I, j less than or equals to I, j plus plus. If c of j means you have one possible value. What is that possible value? Pos dot pushback of mask reminder 1 power j probably, right? If j is 1, you have to take reminder with that power. With that power, you have to take reminder. Plus mask you have to subtract everything else by 2. Okay, let's just make it like this. Int rem equals to mask left side equals to left equals to mask reminder of 1 power j, and then what happens, the value will become int val equals to final value will become mask minus left by 2 plus left, right? This seems okay. We are removing that, we are subtracting it by 1 and then we are just putting it back. Okay. Is this clear, guys? Pradeep, Pradeep, it's just brute force, okay? Pradeep KR, we have configurations of 1 comma 2. It's game, okay? I tried thinking about the game, but then it was for games. Let's say you can remove this or you can remove this or you can remove this. Okay, you can remove this or you can remove this, and then you will get the new configuration, right? It's a game, it's symmetric. You can just see this thing, okay? What are the possibilities of first player? It max n possibilities, right? And among all of them, after removing that, the new configuration, if second player loses there, then he wins. If at least one of this is losing for second player, he wins among all possibilities. If none of them are losing, that means he loses because second player will win. So that's it. This thing we are trying to brute force, okay? Guys, don't spoil C for me. I should not look at the chat, I think. Okay, now we have these possible values, right? So what do we do once you get a possible value? You have answer. So even if one of them is losing, even if one of them is losing, even if one of this val is losing. So how do you convert that val again? You will convert that val into its complement. Why? You will convert that val into its complement because I'm just subtracting with this to convert it into complement. Okay. Is this clear? I think someone else was following, right? Ajay. So we have val remind val. I'm trying to complement because now Bob is playing. Because of that, I complimented. Because now twos or ones or twos for Bob, right? Complemented because now Bob should lose. Okay. Now dp of I of mask equals to or equals to will Bob lose is the question, which is dp of I minus 1 of if Bob lose at least once, we are winning. Will Bob lose? That's it. If Bob loses at least once, we are winning. If Bob is winning every time, then whatever you do, you're losing. And what is the Bob's configuration? Possible. These are possible things you have. Possible things you have after removing that, and then for each possible thing, I'm just flipping because now Bob is playing, and then this ball is primal, my grinding jaw, the head full of nectar on my bedroom door. Okay, done. Now what do we do? We have a DP. What do we do? This wall is primal, my grinding jaw, the head full of nectar on my bedroom door. So implementations are not complex always. They're like simple, clear and clean implementations, right? Answer plus equals to dp of n minus 1. Everything is there. And mask. Number of times allies will win, right? 2 into. Okay. Answer equals to 2 power n. Because if Bob wins, answer is 1. Allies wins, answer is 2. So instead of that, instead of 1 comma 2, we know the total number of things is 2 power n, right? So I'm writing it directly here. 2 power n, I'm writing it here instead of 1 and 2. Now it's just plus this. So let's see if this works. See, it's working. Should this be I plus 1? Why we have I things? No, that is I. That is I. Mask reminder J. Okay. I'm using to complement because you have 0, 1 up to so on I. Okay. Now you have just this. One has been reduced. So now you are just taking all of them as ones and then you are complementing. Among all possible configurations, how many bits do we have? I minus 1 bits, right? This will have I minus 1 bits. And I minus 1 bits, we are handling I minus 1 bits. So what's wrong? 0 bits, wait a minute. 0 bits will have two things. 0 to there. Something's wrong here. 1 minute, let me check carefully. The headache till the necktie on my bedroom door. This will have I minus 1 bits. I is there. So for 2 power I minus 1 things, we should be computing. Guys, I am also here. Don't talk with yourself. This wall is primer, my grinding jaw. The headache till the necktie on my bedroom door. Okay, for 0 we are having 2 power I plus 1 number of things, right? So here, after you remove that, how many bits does this have? It will have I bits. These are I bits, right? These are I bits. And we have, for I minus 1 will handle I bits. That's correct. Everything is right. What's going wrong? Okay, I'm not initializing shit, right? You guys are not helping me at all. Headache till the necktie on my bedroom door. My conscience crying. My eyes are too curled up in a. Oh, oh. So now what's wrong? For 1 comma 2, 3 comma 2, 2 comma 1, what is this? All can be taken, right? All can be taken. Whenever all can be taken, what's the answer? No, not all can be taken. Only the first two things can be taken. First, remove 2 power 8. There are 4 winning positions for 2. There are 3 winning positions for 2. Okay. All 2s is winning. 2 to 1 is winning. No, no. 2 to 1 is winning. 1 to 2 is winning. Okay, there are 3 things. 3 winnings. I am finding 4 winnings. Let me just output what are all winning. Zero is winning because zero means all twos. No, zero should be losing, right? Okay, I cannot just subtract this thing. After applying that, I have to also apply. I have to make that bit zero. I have to make that bit zero. But how? I have to make that bit zero, right? If that bit is active, if the bit j is active, just subtract that or XOR it. I was not able to remove something and then merge them. I don't know why I'm like this. So right, we have removed that, and then it's just right by 2 plus left. How is one winning though? One means just 2-1-1, right? How is 2-1-1 winning? Guys have to sleep. What do you mean? Why don't I reply? My grinding jaw, the headache bullet that turned on my bedroom door. My conscious body, my eyes saw too. Curl up in a hot. Uh, 211 has been shown as winning. But how? He can always remove this, right? 211 should not be winning. Means we got that. We got that. Said I do. This soul is Brahma. My eyes are two. Cuddle up in a hot dun, dun, dun. Said I do. That was the error. Okay. Guys, that was the error. So now even will pass. X minus minus was the error. And now we do E2. How do we do E2? We copy paste this shit first, okay? We copy paste this for E2. And then we want, let me call this thing. Let me call this as G of Z, okay? Let me call this capital G of Z. G of Z equals to dp of summation mask len equals to Z, okay? This wall is primal, my grinding jaw, the headache will the nectar of my... What all do I need? It's just powers. What all I need is just powers, right? It is m minus x plus 1 whole power z. We have many different values of x and we want to power them very quick. We must use binary exponentation. We cannot just maintain arrays because for each x you want, we don't need binary exponentation because z is small, right? Z is small. You don't need any binary exponentation, okay? You can just compute f of z for each m, okay? It's not that difficult. So now what do we do? I'll first maintain g of z, which is g of number of ones, right? What is that built-in pop count? I don't know that. I can do this, but light. Now what should we do? We have g. We just want f of z for each x, right? X equals to 1, x less than or equals to m, x plus plus. For all of these x, what do we want? First I will find f of z, okay? So how do I find f of z? I will first find m minus x plus 1 for everything, okay? By making f of 0 equals to 1, and z can take values from 1 to n, right? 0 to n actually. M minus x plus 1. Okay. Now I will multiply uh, now I will maintain another value for power of x minus 1. Okay. I will maintain power of x minus 1. Okay. For n it should be 1. In power of x minus 1. Power of x minus 1 equals to 1. If I z equals to n, in reverse way I'm maintaining that z greater than or equals to 0, z minus minus f of f of this fall is from my chronic joke. F of z times px m1 reminder m. Okay, done. Px m1 equals to power of x minus 1, right? Okay, done. So now we have f of z. We have f of z. We are not even using binary exponentiation type of things, okay? What is answer? Answer is for x it is f of times z, f of z times g of z, right? F of z times g of z. Okay. Int int count greater than x, config greater than x, okay? Or we can call it dp2 dp greater than or equals to x things. dp of m plus 1, okay? Where answer is greater than or equals to x is what we need. Answer greater than or equals to x means dp of x, okay? Answer greater than or equals to m, answer greater than or equals to x is that, okay? So what is this? Fall is primal. dp of x is 0, and then int let's just make it again pos equals to mm, 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 f of z times g of z pos reminder equals to m, okay? G of z is number of active binary strings of length this much. F of z is number of all possible configurations that map to one binary string of length z. And now we have pos reminder, and then that's it. That's the answer. Okay, now I have to add that. dp of x plus equals to pos dp of x reminder equals to m. Done. Now what do I do? Int I equals to x equals to m minus 1 x greater than 0 x minus minus dp of x equals to dp of x minus equals I should not come from back. I should come from start. Okay. So now answer. Let me call it optimal. It's not optimal. What is that? Games maybe? Games where X will win. Games is also bad variable. See, DP exists because people can't name. I told this already. This was working, right? Guys, is anyone here? No one helping me, lol. It's giving error here too. But how? Why? Why can this be error? Just copy paste it, right? Down on my bedroom door, my eyes on you, cuddle up in a hug and why? Is the input changed? N M. See, I'm writing here, guys. I'm writing at 139, and it is failing in. Where is it failing? Okay, I think it's just memory limit exceeded. I'll keep it out. This cannot be like that. X minus m minus x plus 1. So the number of things where answer is greater than or equals to 1 is more, and number of things answer greater than or equals to x is more. Small is Brahma, my crying ninja, the headache pulled the necktie on my bedroom door. You're done. So guys, let's go to C. Okay. Where are my viewers? It's one sleep. I have work tomorrow. Yeah, it's done. Let me try C and A. Okay. Let's define the function f of A as of a, for an array of length n as cost plus alternating sum. Actually, now consider the scenario where Alice and Bob are given an array of length n. People might have hated Alice and Bob after this contest. They play a game. Everything is a game. Taking at most these many turns alternatively while Alice goes first to perform one. I like how challenging are these problems. Like they don't go easy, right? Like they don't give you familiar terms all the time. Like if someone starts new, they want to see binary, they want to see linked list. They can't see linked list here, right? I like that. Like I like that it's a bit. In each turn, they must perform only one of the following operations. In the game, for both Alice and Bob, choose integers L, R such that swap AL and AR. This adds R minus L to the cost. So you're swapping two things and then it adds something to the cost, it seems. Okay. Assume that Alice tries to maximize f of A and Bob tries to minimize it. Your task is to determine the final value of f of A, assuming both players play optimally. This can be anything. AI can be very big. So, but the cost can increase at max by n, right? Cost can increase by at max n. So, Alice wants to maximize that, but anyone can end anytime. So, anyone can end at any time, right? This means after first round, Bob may reduce something, and then if Alice can increase it after Bob reduces something, see, the fact is that Alice can, if it goes indefinitely, Alice will win. If it goes indefinitely, Alice will win because Allies can keep adding these costs, right? Costs keep adding, but then this is fixed value. Even if you rearrange them to the best, this is a fixed value. Okay, so so after both of them played one game, let's say, okay, let's say now we have initial cost. Now we have initial f of a. Now we have initial f of a. Answer is at least more than this. Answer is at least more than this. Otherwise, Allies will end right now. Okay, because both players play optimally. Answer is at least more than this. Okay, and Allies will do one cost. Okay, Allies will do one cost. Now Bob's turn. Allies will do one cost. Now it's Bob's turn. And Bob, answer is at least more than this. And now Bob will make sure answer is at least less than this. I'll just write that down. Okay. This one is prana. Answer, let's say f of a is initialized did a move means final answer is greater than or equal to f of a. Now f of let's say f1 of a after one move of Alice. Now Bob did a move means means answer is less than or equals to f1 of a. Why? Because Bob wants to minimize it, right? Because Bob wants, if answer is less than this, Alice would have ended the game. If more than this, Bob would have ended the game instead. So now answer belongs to be these two things, okay? If answer belongs to these two things, that's one thing we can say. Now, okay, answer belongs to these two things, okay? Answer belongs to these two things, okay? Greater than or equals to f of a. Now we have f2 of a. Bob, if Bob can reduce, okay, let's say Bob made it f2 of a, okay? Now again answer will become greater than or equals to f2 of a, okay? So Bob must reduce that. Means Bob will do this only if f2 of a less than f1 of a. Even if it is equal, he can just end it. Right? Even if it is equal, he can just end it. Bob will do a move only if this, even if it is equal, because after Alice get a chance, she will proceed only if it's going to be more, right? So Bob did a move means f2 of a is less than this. So can Bob make it? Can Bob make it? Can Bob reverse whatever Alice does? Then the cost will increase, right? Okay. After Alice has done a move, let's say somehow Bob was able to reduce the cost a lot. Bob was able to reduce the cost a lot, and then Alice, whatever Bob does to reduce the cost, whatever Bob does to reduce the cost, Alice can reverse that and still make it a bit more. Okay, Alice has more power. Whatever Bob does reduce the cost by doing same swap. So there is no point of Bob doing a move. What the fuck you do? Alice will do something better. So can't do nothing. Alice is too powerful. Feminist world we are living in these days. Than Bob. Answer less equals to f1 of a means only one move will happen. Bob will end after that. If Bob did a move, that's not good because Alice can reduce and bring back the cost down to the same value that was before and make the cost more. So the problem is obvious a bit. Okay. Why did someone take? I remember someone telling they got the idea in 10 minutes, but then they were of this after move one. So now you want to find what's the maximum value after move one. Okay. Maximum value after move one. Okay. This is also not that easy to compute, right? N is less than or equals to 25. Now let's just let's just say Alice chose I comma j. Answer equals to j minus I plus answer equals to j minus I plus uh, f of a plus j minus a plus. What's the difference now? What's the difference of a? It is minus 1 whole power. If you consider zero based index, minus 1 whole power j times a of j, right? This was the initial weight. Okay, this was the initial weight that was there. But now these things will get flipped. What happens initially in this position? A of j was there, but now what will come here? A of I will come. Okay, and here initially in this position a of I was there, but now a of j will come here. Okay, so writing things down, I less than j, let's say. uh, Alice can always choose L equals to R. Answer equals to at least f of a, because when because they can at least he can end it also, right? Instead of swapping, he can end it also. Now we have this. When we have that, now maybe I will brute force on evens and odd things. I being even, j just brute force that. Then what do I have? So if I write it again, okay, if parity of I comma j is same, then this shit is 0. Then answer minus I. Okay, which means answer is f of a plus parity is same n. If n is odd, n minus 1. If n is odd, this is the best, right? If n is even, if n is even, this is the best, right? Probably the longest subarray. Now, if one is odd and the other one is even, if one is odd and the other one is even, then you have this thing to be plus 1 or minus 1. But then you know these two are not equal. Okay. Maybe now you can brute force j being even, I being odd, j being odd, I being even. So how is it so far, guys? Screen on. How long back did it gone? Yeah, how long back did it go? So now we have this. So what I wrote was fuck. So what I wrote was I wrote a lot. I wrote a lot. I chose J. I have explained that Bob will not make a move because whatever Bob do, Alice can reverse that and then increase the cost. So Bob doing a move is useless. So Alice does a move. And if Alice does I comma J, what will happen? J minus I will be added to it. And then what will happen? Initially, in this minus 1 power j position, zero based index, of j was there, but now a of I is coming. So it is a of I minus a of j. Okay, and here, damn guys. So now we need something in opposite parity, right? So let's just take j to be odd. J j is even. If j is even and I is odd, what happens to this? F of a plus j minus I plus j is even. So it is a of I minus a of j. And it will just become twice because the both will get added up, right? Whatever this is, this will be the same. Or else you guys can check because this is opposite, this is minus 1. And then this will just add up. Flip and then add up. So here what do you need? When j is odd, you need 2 times a of I minus i's. It's f of a plus j minus 2 times a of j plus this h. So you want this maximum value, okay? If j even, if j is odd, then you have f of a plus j minus I minus 2 times a of I plus minus a of j. You want this thing now, which is nothing but f of a plus j plus 2 times of a of j minus 2 times of a of I minus I. Okay, you want maximum of this for odd things. You want minimum of this for even things. Okay, so for odd you want to maintain this, right? For even you want to maintain this in one based indexing, and you want to maintain maximum of both. So okay, int n, cin n, int a of n. For int I equals to 0, I less than n, I plus plus. This is what is needed, minus 2a minus n plus 2a minus I. I'm sleeping. I will quit these streams, guys. I cannot do these streams for long. Okay. You guys will get this only for a few more days, probably. See, I must quit. With wrong answers coming. I must quit CP2. Ultimate value. Make it 60 likes, guys. Why are you waiting at 59? Can you guys make it 50, 60 likes? Yeah, okay, sure. I'm just joking. I have to quit CP2, bro. What's this wrong answers? And then still not. Still not. Guys, does anyone see what's the error? I have considered these optimals, right? I have considered those optimals. We have considered initial cost. And then, if n is odd, same parity will cancel out. I, comma j being same parity will cancel out, and then the max value is this. If n is even, then this would be a max parity. This wall is primal, my grinding jaw. The head till the necktie on my bedroom door. My grinding jaw. And then what is this? If I mean, those are the values we are proceeding further to, right? I think this is right. Odd should be minus 2i minus j, right? No, odd is being positive. Is this wrong? It's being minus, right? See, both are minus. Let me solve a. Okay. Okay, I know this thing a little bit. Okay, for binary string. Damn. Okay, let's see what happens. 1 1 1 doesn't change anything. 0 0 0 doesn't change anything. If it is only one, if it is 0 1 0, if it is 0 1 0, uh, right shift or left shift the values cyclically. How many times can we do that? Only once or what? This comes here. Okay, we cannot do more because that's all we can do. So what happened? It comes here. It comes here. So this thing came, and we can do this anywhere. Okay, we can take it any subsequences, and then as long as there is a 1 and 0, there is a 1 and 0, size greater than or equals to 3. There's a 1 and 0, 1 1 0. You can move 0 there and you can move 1 here. Okay. So for all the zeros, while they're coming forward, they could have come they could have come by taking two ones in front of them. Okay. They could have come by taking crossing two ones in front of them, but then there is only one one. It can cross it. Okay, let's just say all of them have crossed those two ones. Why is it complex? It should not be complex, right? So we can swap things. Okay, we can swap things, not just whatever the logic I was applying was for adjacent things, right? For inversions, kind of adjacent things. But then you can directly take, uh, okay, you can directly take ones and zero that's not in its position. Okay, take a one and take a zero that's not in its position. We have to swap these two, right? Take one more thing that's not in its position. Okay, now we have three things which are not in its position, right? If you have three things which are not in its position, so let's say you have you have one one zero, three things not in its position, or zero one one. As long as you can take three things that are not in their position, you can do shit. You can only make them zero one zero, zero one one, right? Or you can make that one zero one. Yeah, you can do shit. Even if it is 100, you can't do shit. You can only change, you can only swap two things. This is unnecessary. The middle one is almost unnecessary. Okay. So now you look at this case, 0 1 0 1. Can you take these three things and then, yeah, so middle one is just unnecessary. So number of zeros not matching and number of ones not matching, that's the answer. Okay. Is that right? Everything's matching. Okay. Yeah, number of zeros not matching and number of ones not matching is the answer. Okay. I can sort. I know sorting is not the required complexity. I should have just looked at all possible things, right? I should have just looked at all possible things. I started initially, but then I didn't look at them. Because if there are only three things, if you look at all possible things, why is it not letting me submit? Guys, anyone debug my C? 28 people at 2 o'clock is unhealthy. This is the best possible thing you can have, and this is also the answer for all same parity things. And now we are left with only different parity ones, and then for different parity ones, this should be the answer. Let me go to test case then. I don't want to see test cases, but then second numbers differ. Is this the test case? Answer is one, it seems. Okay, I thought I will just start from here, right? I'm missing 0 comma 1. I'm missing 0 comma 1. I should start from 1. I'm starting from 1. Okay, I have to initialize E to something too big. No, something too small. I thought, I thought, I thought because I thought I'm going over same parity. That's why I went to 2. But then I was going over opposite parity, right? So I should start from 1. I thought I'm checking same parity thing, so I went from 2. Okay, let me sleep, guys. Thanks for staying. Thanks for viewing. Thanks for liking too. It's too much. 66 likes is not normal. I think it blow up some. Not blow up, like it algorithm showed to more people. I think that's the reason. But then why would they like? Okay. Anyway, I cannot do D. I'll come some day later. Bye. Thanks. We have A, B, C. We have A, B, C. Even E2. Even E2 seems easier than D. You guys should see, right? Even E2 seemed easier. Thanks, guys. Combinatorics is something anyone can learn. It's not that serious. Everything is anyone can learn. Like if you put something and then do something. Bye. Good night. I'm not in. I want to maybe. Bye. Good night, guys.